So we were talking about the diaphragm maximum average drift ratio. This is a purimunta sukatalega na. Hello.
No, sir. Let's start now.
So for the maximum average displacement of the diaphragms, you have to go to the display, show tables, and click on the analysis, and then go to the results and click on this diaphragm maximum average drift, right? And click on OK. So it will show you the drift for the each story, right? So this is the maximum, this is the average, and this is the ratio, right? So you have to copy this. Let us go to this. We need to story, and we load combination, and then this is the for the diaphragm maximum, average, and the ratio, right? So we have to select all of these from the top to the bottom, and we'll copy this and we will paste in this sheet, right? So you can see there is no warning for the irregularity, right? So for the confirmation, let us write 2. So you can see it will show you that your structure is irregular, right? So if I keep on increasing its value, it is greater than 1.2. So it will show me that your structure is irregular or extreme irregular, right? So if this ratio is greater than or equal to 1.2, it will take as regular. If it is greater than 1.4, it is extreme irregularity in your building, right? So in our building, there is no irregularity, so it is not giving me any warning. So let's go to the Y direction, and we will select this earthquake Y, right? And then we will select the diaphragm in Y direction. So again, we will select the from the top, and then we will select this ratios, and we will insert these in our table. So you can see the ratio for our building is less than 1.2, right? So if I confirm it, so let me write 1.3, 1.4, 1.5, 1.6. So it's giving me the warning that your structure is irregular or extreme irregular, right? So this is the whole story, how to check the irregularity, torsion irregularity in a structure, right? So the next part is that if torsion irregularity in your building is greater than the limit specified by the code, so there is a section that is 5.30 to incorporate the effect of torsion irregularity. So in our case, there is no torsion irregularity in the X direction or in the Y direction. So what if there is an irregularity in your building? So codes give the solution for that. When torsion irregularity exists as defined in table 5.12, the effect shall be encountered for increasing accidental torsion at each level by amplification factor AX. So this is the value, the factor AX, it is known as the amplification factor for the torsion irregularity. For the we have used in our earthquake definition torsion eccentricity. This is the eccentricity torsion it is talking about. So it is equal to the delta max divided by 1.2 times delta average whole power 2. And delta average is the average displacement at the extreme point of the structure at level X. And delta max is, this is the same we have inserted in our Excel sheet, right? So you have to calculate this. So let us go to our, let us assume that we have our torsion irregularity in X direction, right? So let us increase it 2.21. So increase it 2.4, 1.23, 1.4, 1.3, 1.32, 1.23, 1.24, and so on, right? So if there is irregularity in your structure, then you have to go for this section which is defined by the code. You have to calculate this amplification factor. How do we calculate this? So there is already built-in Excel sheet for you. You can see this formula has been used to calculate the amplification factor. So it is calculating the amplification factor for each story, right? And then how to calculate the new accidental eccentricity. You have to multiply the previous one used in your definition of the earthquake loads. Let us go to the ETAB and go to the define load pattern earthquake X, modify. So now you can see that eccentricity is 0.05 is used during the design of this building. So you have to multiply this eccentricity with the amplification factor, that is 0.7. So these are multiplied and you will get the new eccentricity value for the irregular structure, right? So you can insert each story eccentricity value one by one, or let me go to this unlock model. You have to go to the load pattern earthquake X, modify. So this is the new eccentricity value is for each story is different. So you can insert each eccentricity new one by one to each story by going into the overrides written in here, override eccentricity. Click on this. So you have to insert the different stories. You have to select that story and you have to insert that eccentricity, right? That you have to give the length, right? You have to insert all of these value for the diaphragms, right? So another option is that you select the maximum new eccentricity value from the given list that is calculated from here, that is new maximum eccentricity, that is 7%, right? So you have to insert this new eccentricity for the, in case of the irregular structure, you have to insert 0.7 in here and then click on OK. So the torsion irregularity will be incorporated in your structure building, right? So this is how you check the irregularity, and then there is a solution for the irregularity, right? So again, if there is another restriction of the code on this factor, amplification factor, I haven't included in here, that this amplification factor should be greater than 1 but less than 3. So the value of AX will not be, should not be greater than 3, right? If it is greater than 3, then you have to select the value 3, right? So this is how you incorporate the torsion irregularity checks in your building, right? So the next one is the design of column. The code limitation for the design of column is from 1% to 8% gross area of the column, and it is defined in section 10.6. And this is the section from the code that the minimum maximum longitudinal reinforcement for the non-pre-stressed column, right? And for the pre-stress, this limitation is for the pre-stress. For the non-pre-stress is 0.01 AG, but shall not be greater than 0.08, which means 1% to 8% is the maximum limit in our column for the longitudinal reinforcement. So let us go to the ETAB and click on the design. So we have to go to the design, click on the concrete frame design and go to the view revised preferences. So from here you can select your desired code on which you want to design your frame SMRF or whatever you are designing, and keep this by step, and all of these by default values. These are from the code, right? So click on OK, and again go to the design, concrete frame design, and you have to click on the select design combination. If you want to select a specific code combination or load combination for the design of the frame. So we have defined these combination for our building. So we have selected all of this. If you want to remove this, you can remove these, right? So if you want to select this, you can move it here, right? On the right, it means they will design your beams and column for this combination. On the left side, it means you have not will not use any combination which is listed on the left, right? So click on OK, and again I go to design, concrete frame design, and you have to click on this check design command, right? So it will start your design of the frame for the beam and column. So while it's doing the design, if you have any questions, you can ask.
Hello, sir. Hello.
Hello, Gigi?
Yes, sir. Yes, sir. I wanted to ask you, sir. In my country, there is no earthquake and wind load. So, does I need to design to check drifty and torsion irregularity?
So there is no what in your country?
In Somalia, there is no earthquake and wind load. Maybe wind load, but there is not much earthquake. So we don't consider any earthquake. So does we need to check the torsional
No, you do
irregularity and
not.
drift and displacement?
So then there is no need to check your drift and torsion irregularity because you are not designing it for the earthquake. You only go for the gravity load combinations. These checks are for those buildings in which you are considering the earthquake and wind loads. Because you have seen that we have checked the drift and the torsion irregularity for the load case of earthquakes, not for the gravity loads or the other the gravity loads.
If I design only gravity load, what checks should I need to do? What check? What kind of check is that I can do if I only consider gravity load?
So there is no, these checks are for the seismic design of the building. So there is no such check for the gravity loads. For the gravity loads, there is only checks for the serviceability, that's deflections, which we were doing in our last session. So you have to check the deflection. If it is in the limit, so you will go for it.
Is it possible to consider a 7-story or 10-story building without earthquake in any country, in any place? Is it possible to consider no earthquake to design?
Normally, the earthquake is unpredictable. You can see that many of the places that were considered as a zone 2B, now they're the new code in Pakistan, they are considered as a in zone 3, because many of the earthquakes have surprised the engineers that they were not expecting that much magnitude earthquake in that region, but it happened. But if you design your building, for example, in your region there is no earthquake, so if you design it for zone 1, so it is very less comparatively to the zone 3 and 4, it is very less forces. So if you design it for zone 1, so you will be on the safe side. If the unexpected earthquake occurs in your region, so your structure will bear those forces coming from the earthquake.
So it's must to do small consider for earthquake. If there is no any kind of earthquake, must consider small earthquake.
If there is no earthquake in your structure, then you are on the safe side. You do not have to consider any earthquake in your design. Go for only for gravity loads.
Yes, because I'm asking you that question because last 50 years in my country, there is no kind of earthquake. Not happen. Last 50 years or last 100 years, there is no any.
So then the design in your country is very easy.
Yes, it's much easy. Yes.
Yes. So you have to design for if there is no, there will be no earthquake in your load combinations. So you have to select those combination accordingly for the design of the frame, or you're designing your slab or shear walls. So there will be no issue in the drift. So you have no issue for the shear walls where you have to put the shear walls, right? So for the design of the earthquake, if you are designing for the seismic forces, then you have to go for the shear walls and torsion and drift, all of these.
Okay, sir. Thank you.
Hello, sir.
Gigi?
Sir, what in case of drift in Y direction, what are the checks then applied?
We have checked our drift in Y direction. There was no issue in our Y direction, so there is no other checks.
If there is some.
If there is some issue, so likewise we have provided shear walls in the X direction, you have to provide a shear wall in the Y direction. in this direction, you have to provide your shear walls.
Same
Normally
procedure.
when you have both in both directions you have drift issue, normally L-shape shear walls are provided at the corners of the building, so it will control your drift.
Okay.
Right, sometimes a core wall is provided like the left wall to control the drift in the both direction. So it will depend upon the availability of the spaces and the approval from the architect.
Sir, does architect design do structural design?
Architect cannot do structure design. He only do the architectural design. For example, he will say you the for example, you're designing an apartment building. He will say there will be 2 rooms and 1 bedroom and 1 lounge, and there will be kitchen and there will be washroom. So he cannot design the architectural design of the structural design of the building. The structural design will be done by the structural engineer.
Okay, sir.
Right. Same for the structure designer. He cannot understand the architectural drawing to design how to design the architectural plan for a building. For every person is born for their job only. So the analysis has been run. So now let me show only the columns, because we are doing our design for the column, and let us disappear the openings as well. So now you can see the elevation, the reinforcement in your column is given by the ETAB. So this is the 9. You can see in percentages as well by going into this. You can see this logo. Click on the display design information. So a window will appear. So it's showing the design output, that is the longitudinal reinforcement. You are seeing longitudinal reinforcement. So let me cross this. And if you want to see this in percentage, because we have restriction in percentages, so it will be a bit easy for you to see the bar percentage. You click on apply. So now you can see that the reinforcement is 1%, which is the minimum reinforcement of the ACI code, right? So you have to check it for all the beams. Let us go to another elevation. So now you can see there is 1% of reinforcement it is asking from us. If there is more reinforcement, let's suppose 1.9 or 1.6, so you have to go for that and apply for the rest of the length of the column, right? So now you can see in our case it is 1%, but on the right side there is asking 1.62%. So let us check the section. So you can see the details by right clicking on the member. So this option, this window will appear, and you have to click on this summary. So this is the summary in which the column size is 36x36, and all other what is the load combination that is governing for the design of this column, and this is the length, and these are the section properties. That is FC prime is 6,000, Fy is 60,000, and these are the design parameters. And this is the information about the axial force in bending moment demands on the column, that the rebar area is 14.5 and the rebar percentage is 1.62%, right? So whether you have to provide this 1.62% in your column, or you can increase the dimension of the column, or you can increase the FC prime, or you can increase the Fy in order to make it 1%, or if you want to reduce the reinforcement, right? Another important check is the beam column capacity check, right? So this is most important, because we will be not designing our beam for the torsion in case of the earthquake, but if you are designing your structure for the torsion as well, so then you have to select only the gravity load combination, right? So the beam column capacity has to be checked for the torsion, earthquake, all of this combination, and this value should be less than 1, right? So one means that the capacity of the beam is greater than the capacity of the beam, so it will be always less than 1. So if this value is greater than 1, it means your beam is strong and your column is weak, which we do not in our structure, right? So this value should be less than 1. So in our case, the minor ratio in minor axis, the capacity capacity ratio is 0.127, which is less than 1, so we are on the safe side, right? The next check is the joint check, because the joint is the critical portion in which all the capacity energy will be dissipated of the at the joint. For example, there is an earthquake on your structure, so the forces will come to the slab, and from the slab it will be going into the beam, because we have designed the slab for the shear, and the beam will transfer this shear demand to the joint. So joint is the critical portion in which all the earthquake forces or energy is dissipated. So this is shear ratio, which is unitless. So this is also the check, which should be less than 1. If it is greater than 1, then there is an issue, and it will show you the failure of the joint or the beam or column. So these two values should be less than 1. This is the critical check, and this is the longitudinal reinforcement, which is 1%, right? 1.62%, and this is the rebar area. The next one is the another factors, which is taking it from the code. The next one is the shared design of the column, which we will talk about after the design of the flexure reinforcement, right? So let us cross this, and we will go to another one, another elevation. Again, we have 1%, and here is in this column there is asking about the 2% of reinforcement. We'll go to the summary, and in this case the load combination is governing is 0.9 and dt, right? So whether you have to provide this 2% reinforcement, or you can increase the FC prime to 7,000, and you have to change the section from 30, 32, 36 or 36, right? So first of all, you have to, in our case, we do not want our structure to be uneconomical. So we don't want to provide 2% reinforcement in our building, in our column. So we have to change this section from 30 cross 32, 36 or 36, then it will give you 1% reinforcement, right? The next is the another grid, which is giving 1%. So in few columns, it is giving me 2% or greater than 1%. So you can provide a 2%. Code allows you to provide up to 8%. But for the economy purpose, you have to increase the thickness of the column. So it do not have any impact on the economy that much as compared to 2% of the reinforcement. So let us click on this. Please turn off your mic, please. So let us click on this and go to the summary. And this is our 36 column, which is giving only 1% reinforcement, right? So let us go to the presentation that we have. The 1% is the minimum and 8% is the maximum. So, right, so these are the different column combinations for which I have calculated the S maximum value for 36 or 36 is 103, and the minimum is 12.92. Same as for the 30 plus 30, the maximum is 72 and the minimum is 9 inch square. And I have written it for the economical purpose, that if you want to assign 24 plus 24 or 27 plus 27 or 18 plus 18, you can also calculate the S max and minimum for the these columns. So in our case, 36 or 36 is 12.96 inch square, and ETAB is asking me about this. You can see that 12.96 is giving me ETAB is giving me this much reinforcement, is minimum reinforcement, right? So you can write this. ETAB is giving me the longitudinal reinforcement equal to 12.9 inch square, right? This is for the 30, 36 or 36. So I will modify those columns which is giving me 2%. I will replace those columns by 36 or 36 section. But we are not doing it here because we are going towards the whole procedure, what is the design for the column, right? So this was the value for the 36 or 36. Let us go to the edge one. This is the 30 plus 30. This is 30 plus 30, and its FC prime is 6,000 and FY is 6. All of these properties are same, and it's giving me 1% reinforcement, which is rebar area is 9 inch square. Right, so we will write again for the longitudinal, the reinforcement is equal to 9 inch. Right, so now the next part is for the longitudinal reinforcement is to calculate the number of bars, right? So for 36 cross 36, we will be using number 6 bars, right? So for this, you have to multiply this total area, which is 12.96, and you have to divide that point by the area of the bar. For the number 6 bar, its area is 0.44 inch square. So after doing this, let us do it here. This is 12.96 divided by 0.44. It gives me the reinforcement. It is 29 bars, right? We have to provide 29 bars in your column, but you have to see that if it is a square column, then it should be multiple of 4, right? You can provide in a square 4 bars, 8 bars, 12, 16, 20, 24, 28, and 32. The requirement is 29, but you have to go for the 28 or 32, but we cannot take the 28 because it's asking about the almost 30. So you will go for 32 bars, right? So we will write in here that 32 number 6 bars. These will be used in our column 36 or 36. So these are the practical values. If you're designing your structure, you can provide these reinforcement 32 number 6 bars. For the 30 cross 30, you have 9 divided by 0. You can change the bar size as well according to your requirement. So you have 9. So we will divide this 9 divided by 0.44. So we are getting 20. So again, we have to provide 16, 20, or 24, but he's asking about 20.45. So it cannot be 20. So you have to go for the 24, right? Because if you give 24, it is again in the range of the limitation of the code, right? So you have to provide 24 6 bars in this column, right? So you can also use another bar size as well. Let us use this number 8 bars, which the area is equal to 0.8. So that will be equal to 9 divided by 0.8. This is number 8 bar. This is number 6 bar. 16.2. And this is 0.8. So for this we are getting 16, and for the cross 30 we are getting 12 bars, right? This is 11, so we will make it 12. We are getting 12 number 8 bars, and here we are getting I think 20. These are the 16, so 16.2. So you can use the combination of the number 6 or number 8 bar as well. So you have to go for the higher numbers. You will select the 20 number 8 bars. So you will use this as 20 number 8 bars, right? So this is the whole story about the design of the column for the flexure demand, right? So our final values are these. So you can use these bars practical in your practical design of a high-rise building. The next one is the shear design of the column. The shear minimum reinforcement limits for the RC column is defined in ACI 31814 25.72. Right? So we will check these after we check it in ETAB, what ETAB is saying about the shear design. So first of all, we have to go for this 36 or 36, and we will go for the summary, and we will check for the shear. This is the shear design in which there is a shear demand Pu. This is the shear capacity of the column, for the concrete 5 VC, and this is the shear capacity of the steel, right? So it is showing you 0, 0 and 0, 0. There is no requirement of the shear in this column because the shear capacity of the concrete is greater than the shear demand. The shear demand is 11 and the shear capacity of the concrete is 196. So that's why there is no need to provide ties in this column, right? But ACI recommends to use this minimum reinforcements to be used as a ties in your column. So let us go to another column, that is the H column, and go to the summary. So there is again no demand for the shear reinforcement in the column. So check it in another. So let us check it at the top. So at the top, there is a requirement of shear reinforcement because the acceleration and the story shears are greater at the top. So the shear area is asking about you can see that there's 5 VC is equal to 0 because if the demand is greater, then it takes the shear capacity of the concrete equal to 0 and then give you the reinforcement in the column. So the reinforcement it is required is 0.22 inch square per foot and 0.27 in the minor axis, and this is the major axis. So we have to select the greater one. So let us select the greater one, that is 0.27 inch square per foot, right? So let us write in column 36 cross 36, we have the shear area 0.27 inch square per foot, right? So let us find the spacing from here. We have to find the spacing by dividing the bar size which you are using. For example, let us use 0.11 divided by 0.72 and multiply it with 12. You will get the spacing in inches, right? So how did I select this bar size? This is the bar area of number 3. So this is the requirement. The diameter of the tie bar shall be at least A to B. If the longitudinal reinforcement, if you are using number 10 bars, from number 5 to number 10, you have to use number 3 bar as a tie bar. If your longitudinal reinforcement bar size is greater than number 11, then you have to go for number 4 bar as a tie bar. So we are using number 8 or number 6, which is less than number 11 bar. So we will be using number 3 bar as a tie reinforcement. So if you do this, that is 0.11 divided by 0.27 and then multiply this command, this value with 12 to convert the feet into inches. So you are getting 4.8. So we will be using number 3 at the rate 4.5 inches center to center, right? So this is we are getting 4.8, so you cannot make it 5. We have to go for the lower number in case of the spacing. So we are taking it as a 4.5 inches center to center, right? So this is for the column 36. Let us go for the column 30 cross 30, and you will see at the top if there is any requirement of the shear reinforcement. You can also display it by going into the display concrete frame information and then click on this shear reinforcement and apply. It will show you the reinforcement, shear reinforcement you can see at the bottom, there is no requirement of the shear reinforcement in the column. But if you go up, there is a demand for the shear reinforcement in the column. So we have selected this one, I think that one. So now in the 30x30 column, let us select this column and click on the summary. You will see that the reinforcement demand for the shear is 0.327 inch square per foot, which is greater than the previous one, right? So in this way, you have to check the shear demand in each column, in each base. So you have to select the maximum and apply it on all of the columns, because you cannot do, for example, there is no shear, there is no tie, so code recommends you to provide the minimum tie spacing, which is defined in this slide. So if there is no reinforcement asking, so when you calculate this, so you have to apply it again for all the column. If you are a very good engineer, you have very good draftman, he is able to provide different section with different detailing. So you have to provide up to some story where there is no demand of the shear. So you have to provide the minimum reinforcement of the shear, and then after on those stores in which the shear demand is high, so you have to go for those spacing in which you have calculated in your design. So for the 30x30, its demand is 0.23 inch square per foot, right? 0.34. So we will write here 0.34 inch square per foot, right? So again, using number 3 bar, 0.11, right, divided by 0.34 multiply with bar, will give me 0.11 divided by 0.34, and then multiply this with 12, we'll get 3.8, which is very less spacing. So you have to increase the dia of the tie bar. So right in here, write the area of the number 4 bar, which is 0.2, so you are getting 7 inches center to center. We are getting 3.5 inches center to center if you use number 3 bar, but if you use number 4 bar, which is 0.2 divided by 0.34 into 12, it will give me 7 inches center to center, right? So this is the whole design of the 2 columns from the ETAB and how you check spacing, because if you provide 2.3 inches center to center, so there will be much difficulty during the concreting of the column. So you have to go for the larger spacing using number 4 bar, right? So finally, we will use number 4 at the rate 7 inches center to center. This is not the center to center, right? So this is the whole summary of the 2 columns, 36 and 36, and what are different requirements of the ties and maximum spacing. We will discuss this in another link. So let me stop this, and I will share another link. So we have to finish this beams and column design.